Hi again, everyone. Welcome back to part 2 of a lecture on aluminium alloys. We'll pick back up again where we left off with aluminium alloys. As I detailed in the first part, the strongest alloys are those that are precipitation treated. In this part, we'll cover this process in detail. If you look up material properties in aluminium alloys in a handbook or a database, you'll often see not just the 4-number designation describing the alloy system. There's also a hyphenated designation that's included. The first letter is O, H, or T, or variants of these. These codes indicate the form in which they are delivered or processed to. An H designation means that it is strain hardened, while a T designation indicates that it's been thermally treated. There are a wide range of these types of treatments to deliver a temper, such that if conditions are optimal, you can end up with an aluminium alloy exceeding the specific strength of even titanium. There are many T designations for alloys. During this lecture, we'll look at the most prominent, T6, which specifies artificial aging, and by way of doing so, also cover natural aging. Recalling that a precipitation treatment consists of a 3-step process. Bring the material up to a temperature to solutionize, that is, bring anything that creates a precipitate back into solid solution to create a supersaturated solid solution. Then this is quenched to attempt to lock in this supersaturated solid solution before precipitate-forming species precipitate during aging. The aging temperature inferred here indicates the artificial variant. For many aluminium alloys, in the quench condition, the driving force for precipitation is high enough to occur naturally, that is, at ambient temperatures. Let's have a look at what this process is and what it means for strength. This diagram may seem complicated at first, but it actually demonstrates all the effects on strength with aging time for a given temperature for aluminium alloys. Let's start at the bottom with the intrinsic strength, shown by the dashed line. This is the strength of the base metal forming the alloy, that is, pure aluminium. Any alloying ingredient will cause some solution strengthening, and this effect will be most prominent when a supersaturated solid solution is present, as shown on the far left by the orange line. As aging proceeds, the precipitation process commences with atoms coming out of solid solution and starting to form precipitates. This is why the orange solid solution curve decreases to approach the intrinsic strength, while the pink curve starts to increase. Then, after a period of aging time, the size of the precipitates are too large to cut, and then the bowing curve takes over. The red line demonstrates the net contribution of all of these phenomena. The peak of the red curve is when the mean or average particle diameter is the appropriate size to take advantage of both bowing and cutting. Let's look at this in practice for a specific alloy system. One way to make aluminium castings is with low-pressure die casting. Low-pressure die casting is a cost-efficient way of making large components quickly. The way this process works is that a reservoir of molten metal is pressurized pneumatically and pushes metal through a sprue into a die. When filled, the feed is stopped and active chilling takes over. In about 2 or 3 minutes, around 20 kilograms of alloy will solidify. Once this happens, the die splits and the part is ejected. A common alloy employed with this process is A356. An aluminium silicon magnesium alloy, formulated for castability, or properties that make it easier to flow and fill a mold or die. This process introduces a microstructure that appears like this, a dendritic microstructure, which consists of an alpha phase and a eutectic phase. The former appears lighter than the latter in this micrograph. This describes the initial process to manufacture automotive wheels. As soon as they are cast and exit the die, they are quenched to assist with material handling and provide some flexibility in the manufacturing process. They are then solutionized, quenched, and then artificially aged. From this point, they are machined and then painted. However, in the intervening periods, immediately after quenching in both cases, there can be some natural aging, the degree and extent to which decided by the amount of time before the following step. The first quench after casting doesn't matter, as any precipitation that takes place will be reversed by the solutionizing treatment. However, if it's not artificially aged fast enough after being quenched following solutionizing, then the effectiveness of the whole heat treatment can be undermined. In fact, some paint processes require curing at elevated temperatures. This also needs to be considered when designing a heat treatment. The heat treatment for precipitation looks similar to a tempering process for steel. However, the times at temperature and the temperatures themselves are quite different. Here are some images acquired using an electron microscopy technique, which is able to detect which elements are present for a given pixel. This is our A356 material, which if you recall is aluminium, silicon, and magnesium. The top image shows the as-cast microstructure and demonstrates that the magnesium and silicon segregates, shown by the orange and red. After heat treatment, it can be seen that there's no longer any segregated magnesium and silicon having the same morphology as the top image. It is all evenly distributed throughout. This demonstrates the T6 heat treatment for A356, specifically for automotive wheels. The precipitate that forms is Mg2Si, which provides peak strength in this alloy when it forms a nanoscale morphology. My electron microscopy technique can't resolve things on this scale, so that's why it appears as a relatively even distribution in the lower image. The time at temperature for both solutionizing and aging is intended to make sure the entire component sees a temperature long enough to complete the treatment. Solutionizing is relatively easy, but aging is often the hardest part to control. This is because aging for aluminium alloys continues to take place, even after 2 hours in this instance, albeit at a slower rate. Let's look at this a bit further. Here is a natural aging curve for the wrought 6061 alloy, which employs the same Mg2Si precipitate for strengthening as the A356. Here, the strength only changes minutely, even for a long period of time. If we increase the temperature to 120 degrees, then there is a significant difference. This is why artificial aging is employed. Increasing to 230 degrees, there is a dramatic difference in response. The peak strength that is obtained at this temperature occurs within an hour. However, when left too long, it will actually drop below the as-quenched yield strength. Furthermore, the peak strength that is obtained at this temperature is lower than that obtained at 120 degrees. We could fill in the gaps between 230 degrees Celsius and 120 degrees Celsius and see that there is a trend that starts to develop. While it takes longer to occur, the peak strength is achieved for the lower temperatures, held for longer periods of time. Held for too long, then there is the opportunity for the strength to decrease below the starting point, below the as-quenched state. Aging curves are different for every alloy system. Here I'm showing a 2014 alloy, which has a phase diagram shown at the beginning of this part of the lecture. Beyond the yield strength, I've also included aging curves that show the ductility as percent strain before failure. As strength increases or decreases, the ductility decreases and increases, respectively. Each aging curve has this type of characteristic, where the precipitate starts to evolve, then hits the critical size for strengthening, and then diminishes as bowing of dislocations becomes the overriding mechanism. This is called overaging. For very large components, the entire aging curve can be observed microstructurally, as I've shown below for a thick aluminium 7075 plate. The larger the component is, then the harder it is to make sure that uniform conditions manifest throughout. So the strategy would be to maintain solutionizing and aging for longer periods of time, if costs permit. So as we've seen, heat-treated alloys employ the elements in solid solution to age under carefully maintained times and temperatures in order to achieve specific properties, either an emphasis on strength or ductility. Even though overaging can reduce the overall strength that can be achieved, ductility can be recovered, and stability to the alloy can be restored. Due care and attention needs to be paid to assessing how much natural aging can take place in the intervening periods with these heat treatments for these alloys, and will also have implications for further processing, such as welding or even in service conditions. In some circumstances, the alloy will continue to age in service, even after going through a full artificial aging process. Until next time.